Hey folks, and welcome to High Performance LLMs from First Principles, Session 2. So again, we're calling our goal, we want to learn how to achieve high performance on LLM workloads. And this week, we're really just going to go really deep into single chip performance. So as in the future sessions, we'll build this up, going all the way to understanding multiple chips, hundreds, thousands of chips, and the tools there. But this week, we're going to start with a single chip. And we're going to discover actually that the tools we need to do that are really the same as the tools we need for thousands of chips. So as always, kind of the three things we're thinking about is we're programming, writing code in JAX, predicting, and profiling. And fortunately, this session, we're going to do all three. Cool. And as always, just anytime you have questions, I'm just like, speak up if you could. If you have topics you're interested in, please message me. Got a lot of great questions between sessions. And then do join the Discord. And then this time, they're going to be new exercises. They're going to be real fun exercises. I hope people get the time to do those. Okay, so what is the system diagram for a TPU v4? So this is just one chip system, and it really ships on these two separate things. So on the left, we have the TPU, which is 275 teraflops of compute. It has 160 megabytes of SRAM. So the SRAM is the memory on the chip, and it has 32 gigabytes of HBM on the right. And these are linked at 1.23 terabytes per second for a V4 chip. So why this is so interesting is that the memory is really quite far away from the chip. So that ends up really governing how fast workloads pick. Additionally, you see the SRAM, the fast memory on the chip is like 20th, something like that, much probably smaller than that, of the memory available, 200th of the memory available to the HBM. And that really, again, governs the way we're going to make decisions around here. So let's start by working out a simple puzzle. How long should it take to add A plus B? Zhongwei.
Hi, Rafi. I have a question. Can you go back to the previous slide?
Yes.
So the SRAM you mentioned is on the chip, right? And there's a HBM as a separate place. If there's a RAM on the chip, why do we need the HBM?
Yeah, okay. So what is going on here? Like, why is all of our memory so far away? So these are two separate processes manufactured in two different factories that are connected by what's called a silicon interposer here. And the SRAM, yes, no question. You can put more SRAM on the chip, but it costs, I think, on the order of 100 times as much. So that's why we have some SRAM on the chip using one chemical process. Then we have this relatively small 1.23 terabytes per second connection. And then we have the so-called high bandwidth memory on the other chip. And it's all just a manufacturing.
So that means the HBM is lower cost?
Much lower cost than SRAM, yes.
I see. Thank you.
Cool, great question. And it's still much higher cost than like DRAM that you have in a conventional machine, but much lower cost. Cool. So let's start by asking ourselves, how long should a talk take to just add two vectors in JAX? And for that, I'm just going to switch this up. I'm going to switch to sharing my whole window. And let's just program this. So import JAX. Looks like it's probably coming through. Folks, let me know if it's not coming through. And then we're just going to like this.
The code is very small.
Thank you, Sky.
That's better, thank you.
Okay, so we have a matrix. We're going to make our matrix dim be matrix dim, matrix dim. Okay, we'll get ourselves two matrices. And then we'll just start a timer. Blocking IO error. We'll get ourselves a timer. So start time equals datetime dot datetime dot now. As we go, we're going to improve this and understand some things about JAX. Then we're going to do end time equals end time here. Perfect. And then for I in range 10, C equals A plus B. maybe we should put steps here. And then this will be in business, right? So we're just going to time this thing out. And I just like, quick word of caution. This isn't going to necessarily give us the right answer, but let's just see how we do as we go. Cool. So we're just running things here now. And it's telling us it took 0.0178, so seconds to do this computation. And let's just start by thinking about if that's the right time. So we have two matrices. So the size is, maybe we'll work it out here. Number of bytes equals a dot size, and now times 4, because it is FP32. We're going to do this 3 times. So total num bytes is 3 times num bytes crossing to HBM. And then our total number of flops is matrix dim squared. Cool. So matrix dim times matrix dim. And let's just count out if our average time is this. Let's just count out the various things. So we have average time. We have flops per second. And that's going to be total num flops over the time it took. And then we're going to also have total num flops crossing to HBM divided by average time. So this is kind of giving us 3 cents. This is bytes per second. Cool. And we'll run this. And I think there might be a question. Oops. Gotta close my parentheses.
I think somebody did have a question, but I have one too.
Thank you.
It's okay. I think I answered my question myself. But just to confirm roughly, the 3 times number of bytes is we're reading A, we're reading B, and then we're writing C back to HBM.
Yeah, that's a great point, and maybe I should draw that for us over here quickly. I'm going to just break out of this for a second. Maybe that is the right. Maybe I should just quickly draw that for us. So we have A, which I'll just give us a color for. We have B, which we have a color for, and then they will make their journey over. That's going to be step 1. And then we have to read them both back, the combined result back. And that, as you say, will take three trips. Make sense? And I will work on my pictures as we go here. And there was another question?
I had the same question.
Cool. Thanks for calling that one out. Do folks feel comfortable with that? Zach, I know you asked. I didn't catch the name of the other. Oh, Julie. Julie seems to have a thumb up. Awesome. Great question. Cool. Okay. So now we have this, and we have it in units that I have to admit that I can't read. So maybe we should just why don't we go to the natural unit? So we'll do teraflops per second, and here we can divide by 10 to the 12, and here we can divide by 10 to the 9.
Rafi,
Cool.
I have a quick question.
Yeah, get in there.
With line 24, your teraflops per second, this might be nitpicky, but it's not average time, right? We're looking for the total seconds. Because your average time is divided by the steps. I'm just making sure I'm understanding what we're trying to do.
No, you're asking the right question, but I think that this is right, because we're saying here I'm counting the flops per 1 iteration.
Mm-hmm.
And then I'm saying, and then what we're doing here is averaging out across the 10 iterations. And we're taking the time, so this is the average time per iteration. And then the total num flops, the total flops for one. I guess it should be one iteration's flops.
Okay. Okay. So that's just one step, the number of flops per step. Okay. Okay.
Yeah. I'm just not going to change it because
Yeah, that's fine.
I'm already pretty committed here. But I hope that I hope yeah, the name you're proposing would be way better. It should be like one step flops. Cool. So I maybe should improve my printing. But okay, so the system is supposed to be capable of 1230 gigabytes per second and 275 teraflops per second. Well, when we look at this, well, I can't say we're doing very well on our teraflops per second. We're only getting 0.06, so that's much less than 1%. But in terms of bytes per second, we're actually using the system pretty well. And then the idea is, well, we're constrained, right? We're moving data across this bus more or less as fast as we can. And that then becomes the limiting factor for doing this computation on this hardware. Make sense, folks? I think it's kind of like a key fundamental thing I'm trying to demonstrate here. So just want to make sure.
Am I reading it right that it's 718 gigabytes per second?
Yeah, let's rerun that. I improved my printing, but did not get around to.
Which is less than 1.3 terabytes.
Yes. So we're never going to get past the theoretical physical limit, but we can find we'll get quite close to it. So as you're saying, in this case, right now, this is reporting we're getting about 60% of the theoretical limit.
Is that typical?
Well, the great questions. You're asking the hard questions. So for end-to-end jobs, by the way, the like state of the art is getting 60% of the model of the theoretical flops. But for something like this, we should be able to do a little bit better, Julie. So because I mean, maybe Julie's like actually a plant that I have in the audience, but because we don't like how things are going, why don't we turn on some profiling? So temp profile me. So this is like incredibly important. So looking at your profiles, just like best way to understand what is going on. And let's run this again with the profiler on. So now our start time and end time will be a lot larger. Maybe I should have actually put the profilers outside of the. So you see our times, it actually messes with our times to do it like this because the profiler takes time to start. So maybe I'll just put it like this. And now we can just look at the profiler. So TensorBoard, -- log dir, profile me. So we're just trying to answer Julia's question of like, what in the world is happening in here? And I will open up our handy dandy profile. Cool. I assume folks are, I assume I'm sharing the right screen. You can see the profiler. Folks can see the profiler, okay?
Yes.
What are we doing here? Boom. Cool. Okay, so one thing that's going on is this is saying that it's taking 13 milliseconds.
Can you zoom in a little?
Probably not, but let me try. Oh, I can. Thank you for asking. Okay, this is taking 13 milliseconds. But the way what we reported over here, that things were taking 17.7 milliseconds. Okay, so what's wrong there? What are we doing wrong? The thing we're doing wrong is actually that not all of these take the same amount of time. So what we're going to do is we're going to change our function to have a def f of a comma b, and we can just return a plus b. And then we're going to use this handy dandy function that I wrote ahead of time, and there's probably nicer ones you can find online too, which I have in timing utils. So it takes a function, it takes some args, and then it runs it multiple times. It profiles it, it runs it multiple times. And then something really important it does is it runs it once before it starts the timing. So that isolates the setup time for that first time. So what we're going to do is now run this. We can take this out, and we can do average time equals simple time it. Hopefully, I can timing util. F, and then we have to pass in A and B. We should probably import timing util. Cool. And we have to give it a name. Cool. So now we're kind of doing the same thing, but we are okay, and unfortunately now this returns in milliseconds, so we should just put this into seconds. So now to answer Julia's question, now we're getting a reasonable number here. So this is taking us about 973 gigabytes per second, we'll see, once we're in 970. And that's pretty good. That's pretty close to the physical limit on the system in practice. Cool. So that's adding two numbers in JAX.
Probably a naive question. How do you access the TPU in your demo?
Oh, I'm just SSHing to TPU v48. So I'm doing it via SSH. You can also do it in a Colab or a Jupyter Notebook.
So it's a virtual machine with the TPU allocated?
Yes. Yes, and I'm just VS Code SSH into it.
Got it. Thanks.
Cool. John Fei, what's up?
Hi, Rafi. I have a question. Do you know on NVIDIA GPU, is there a similar memory pattern where there's a HBM?
Yes, it's exactly the same. The different generations of GPUs and TPUs have different ratios, but one of the things that's happening actually is that this number is not changing very quickly, but this number is growing much faster.
Okay.
And but NVIDIA GPUs just the same, AMD GPUs just the same, Intel GPUs just the same. There are chips that just don't have this guy at all, but this is like a chemical process. They're just two separate chemical processes, and they drive this design.
Okay, thank you.
So, for example, the Grok LPU, the Cerebras wafer scale engine, neither of those have the HBM chip at all, but for almost everything else on the market, it looks just like this. Vitaly.
I have a really dumb question. So typically we are reading our data sets through CPU, right? So we'll probably read it into CPU memory and then transfer it into HBM. So, or is it like a direct DMA transfer into HBM? Is there some latency there as well?
No, there is definitely latency there. It can be DMA'd. The key trick, Vitaly, and we will analyze this when we start thinking about the system on a bigger scale, is that usually the inputs are quite small relative to the amount of computation. So even though the pipe is small to get your inputs, it's usually not your limiting factor. But that's the same analysis we're just trying to do with just one axis right now for a whole system diagram. And that's definitely something we're going to cover later on. It's a great question. Cool. Without further ado, I'm going to move on to the next slide. Okay, so I mean, let's just sound this out. I kind of wish I had a poll because this is such an interesting question. But before we talked about adding two numbers, A plus B, and we saw we were able to get within 80 or 90% of the physical limit on the hardware. Now let's think about adding A plus B plus C. How close do we think we should be able to get there? And also, how fast do we think we should be able to go? So, any takers? How long? If adding A plus B takes 1 second, how long should adding A plus B plus C take? Okay, so no takers. Let's just do it the obvious way.
Is it 2 seconds?
That's a good guess. That was definitely my first guess. So let's do it. I think you're going to be right. A plus B plus C. So I didn't catch your name, but some friend in the audience suggested if this took 0.013, we're guessing 0.026. And you're right. Okay, so let's describe the algorithm that's happening. Is now we have 3 inputs. And forgive me for like making such a mess of this. I'm going to make this one yellow. So first we get these 2. So they go boom, boom. They both go to the left. Then we're going to get some sort of like hybrid of them, which I'll just, for the sake of drawing, put it like this. Some sort of like striped hybrid. I don't know how to draw it. Then we add these 2 the same way, and then we finally get our real output. So we have to cross into HBM 1, 2, then write 1 back, 3, then cross back 4, 5, and then write 1 back. So that's 6 paths instead of 3, and corresponding to that time, it's almost exactly 2 times as long. So yeah, great question from Robert Crow. So why don't we keep the intermediate result in SRAM? And the reason for that is because these guys are drawn to scale. They are too big to fit in SRAM. And also the way we wrote this function, it wouldn't happen automatically for us. But mostly, they're too big. Cool. So if anyone wants to propose a faster algorithm, I would love to hear it. What can be stored in SRAM? So we can store whatever we want in SRAM. It just has to fit.
So could you partition the matrix and then store smaller versions?
Yes, thank you, Slava. Thank you, Julie. So that's exactly what we do. So partition. Another fancy word for it, if you want, in this context, is we call it a loop fission, where we're splitting this thing up. Another word for it could even be actually fusing the 2 operators together, or pipelining. So what is kind of being proposed is we window them. So I don't know how to draw this, but I'll do my best. So we basically take a little chunk of the first chunk of them. I'm just going to give up on drawing, folks. I'm sorry. So we take the first little chunk of them, whatever chunk fits, that goes to SRAM. We do the math there. We send it back, and then we keep doing that. And that will get us, instead of doing it in 6 round trips, that can do it clearly in 4 round trips. So it should be 4/6 as fast. Okay. So how do we do that? Seems a little tricky to program. So historically, actually, the way people did this is they would just like write their function, and they would program it by hand. And you can imagine, I think most people on this call can imagine programming it in Python or C or whatever. And maybe I'll just quickly just show you, just like for aesthetic purposes, just be really clear what we mean. If someone's raising their hand, just please speak up.
Oh yeah, quick question, Rafi. So are we loading 160 megabytes by 3 from each of those matrices here?
That's the proposal, yes. Or probably 160 over 4, maybe. But yeah, something like that.
I'm curious, would XLA do any of this for us?
Yes, that's the payoff, Robert. You're in the know. So just to make sure everyone understands what we're doing, the naive implementation looks like this, and then returns boom, returns C. Okay, and we just need to do it like, and then the kind of the fancy, what used to be what kernel engineers would do is they'd be like, oh, you want a fancy one? So I'll do it like this for you. So this is going to be output. And instead of calling simple add 2 twice, so let me just make this a little bit clearer, I will give you a simple add, I'll write simple add 3 for you. And then we can do that just like this, and we will return out. So it's totally something you could imagine programming by hand, but it is a little bit obnoxious. So the way we do this in JAX is this very handy-dandy jax.jit. So there are a couple ways we can do it. Maybe the best demonstration of it would be JIT_f equals jax.jit f. And then we can do, this can be f. And then I'm going to just put this away for now. I don't think we need it. And then we can just do the same thing with jax.jit f. And jax.jit f has the exact same semantics as f, except hopefully in this context, it will be faster. So f still takes 26.23 milliseconds. And then JIT_f, I named the second print badly, JIT_f takes 18.96. And then maybe we should just ask ourselves what's going on here, 26.23. So in principle, it should take 2/3 as long, which is 0.67. This takes 0.72, but still a very, very nice speed up. And actually, the reason we're probably not getting quite the full speed up is that we're VP bound. Cool. So JAX naturally, with the power of jax.jit, is able to do this for us. I just want to give a quick primer on how jax.jit works. One of the things that's really, really interesting about it, so I'm going to just turn off, these prints, and we'll just run JIT_f of a comma b comma c. Is if we like print a, it's going to look totally different. So JAX is actually, when we run jax.jit, it is tracing the function f, or maybe I'll trace it later, but it gets this shaped array, and it no longer can print the contents of our matrix, because JAX is lazily tracing through our function, understanding the computational graph, storing it, and then compiling it. And that's actually really the only way to achieve performance on this workload. I just want to contrast this with if instead of doing JIT_f, I do FABC. Then, of course, when I print A, I will really see the contents of the tensor A. So it's a very interesting optimization that JAX is able to do. It really changes the semantics and the structure of the computation. But it does allow you to do things much, much faster. And this is sometimes called compiled versus eager mode. So this is compiled, while instead of directly running F is eager mode. Cool. So pretty excited about jax.jit. Andy, what's up?
So in addition to the tracing, is it also doing the windowing like during the compile? Like, is it? Yeah,
the compiler, because now the compiler is given the full view. The compiler can look for these optimizations, and the compiler is doing the windowing or the pipeline automatically.
Mm-hmm. Got it.
Great question. You can also, like for debug purposes, do a JIT that doesn't actually have that windowing. That's totally, of course, an option.
Cool. Thank you.
Awesome. And I just wanted to just take a quick second, because I was just praising jax .jit, but it really isn't magic. So hopefully for this particular one now, where we don't need the fusion, so JIT_f equals jax.jit f, hopefully this one, so now I'm just doing a plus b instead of a plus b plus c. Hopefully this one will now take the same amount of time. And the reason for that is because we really aren't doing anything, right? Those a plus b will automatically compile to the right implementation. So there's really, excuse me, this is just a little bit obnoxious. Let me just turn off this print. So it took 26.88. Sorry, that's a little, sorry, I didn't run the computation I wanted to, I'm sorry. So again, here now I have JIT_f of a comma b and JIT_f of a comma b. Cool. So hopefully what this will show us is that they both get pretty close to the same performance. And in fact, they do, right? So they both take just about 13 milliseconds. And the reason for that is what we've already been talking about. There's nothing to fuse. A plus b is the fastest implementation of F. So there's nothing the compiler can do. I'm going to just go back one more time to the previous implementation. So we'll just do this. C and C. I just want to look at that intensive board so you all can just see what is happening under the hood.
I think you have to update the actual computation again.
Oh shoot! Thank you, Sky. Much appreciated. Cool. Let's hop forward. I think we can get to that in a second. Thank you for the tip, though, Scott. So what are we doing? So the word for this can be operator fusion. It's a little bit. There are a lot of actually two different things going on, but this gets more and more complicated. Obviously, as the compute graphs get more complicated, and then making the right choices gets more complicated. And the normal compilers, so like GCC, Clang, all the compilers outside of ML, actually really can't do these optimizations. It really requires XLI or something like it that is able to describe your program fully statically to get to the best performance. So it used to be folks would just like write bigger, well-optimized functions, so like add 3 instead of add 2. But it becomes harder and harder. And then one key observation is the memory bandwidth is growing less quickly than the number of flops. So building these bigger and bigger blocks actually becomes more and more important. So it used to be, and in many cases PyTorch still does, operator by operator dispatch, just dispatching these things one by one. So that would mean these 2 calls to add, and you take 6 round trips instead of 4. But nowadays, PyTorch, JAX, TensorFlow all have end-to-end optimizing compilers. And the compilers can do many, many more optimizations. So we actually saw, I think 3 of these optimizations in action, because there are actually really 3 separate things that we wanted. One is we wanted a fission. So we wanted to break this up and actually to multiple operations. Then we wanted overlapping, which we'll learn about another time. And then we wanted a fusion. We wanted these 3 operations to all become a single operation. So this relatively simple optimization, having it work actually requires a lot of different optimizations within the compiler. So what is the point of this, and how do we think about performance? It's the performance we're going to get is going to be bound by these 2 different ideas. So one is the program's operational intensity, how many flops per byte the program needs, and the second one, and then that will govern the best performance. So for a program that's really bound by peak performance, where the number of flops is really, really high, so over here, we'll get pretty close to the peak performance bound. A program like the program we saw, which is bound with bound, will get a poor performance in terms of flops because we'll be saturating all of the bandwidth. So this A plus B computation was highly, highly bandwidth bound, and it puts it all the way over here on the left. So I think this can be a little bit hard to reason about. So I'm going to try to just do a couple more, well, at least 1, maybe 2 more examples to let us think about whether we're flops bound or bandwidth bound. Cool. So hopping here, we're going to just talk about matrix multiplies. So matrix multiply, so we have a matrix that the left one has rows and columns, the left one has rows and columns, and then for each entry in the output matrix, we take this dot product. So the input, so A is of size X by Y, B is of size Y plus Z, Y comma Z. The number of flops is 2 times X times Y times Z, so the number of outputs is X by Z, and the number of flops per output is 2 times Y, right? Because there's 2 times Y components, and then for each one, there's a multiplication and an addition. And then the output is going to be 2 times X times Z bytes. So we should probably, I guess we should just do so. We should just see how this works here, and maybe we'll just do A times B to get us started, and we can see it also with the ReLU. Cool. This is a little. I'm just going to move this down a little bit. So this is a kind of one option we have. So I'm going to actually switch these. Actually, I won't bother that. So one function we could do here is actually a function we saw a lot in our previous class, is where the function is the ReLU, which is this nonlinearity of A times B. So now let's just calculate our sizes. So A is A times size. Number of bytes crossing to HBM, still 3 times number of bytes. Total flops is 2 times matrix M times matrix M. We can get rid of C. We can get rid of C. And now we can time this out. So what we really want to do is average time seconds. This one can be no JIT. And then this one can be JITted. And we just print out how we're doing on both of those workloads.
Hey, Rafi, don't we also have a flop for each element that we apply the ReLU to?
Yeah, I mean, sure. The thing we're welcome to add that. I usually just don't even count things because remember that's going to be a factor of 32,760 times smaller, so it's a much less
Sure.
than a 1% correction. So, but totally accurate. We can just do it like this. Thanks, Zach. Okay, so now how are we doing? Well, it goes just a little bit faster with the JIT. So I guess I should say no JIT. JIT. So the JIT is able to get us to 256 teraflops per second, and the no JIT only gets us to 248. And then you can see we're actually very close to the theoretical limit. Remember, the theoretical limit is actually 275. So both of these are, within 10% of the theoretical limit, but we're barely even using the bandwidth. Remember earlier, the bandwidth was on the scale of 1230 gigabytes per second, and here we're only using 5% of it. And the reason for that is because we're very, very flops bound. So our arithmetic intensity, which I'll print as well, print our arithmetic intensity, is num flops over total bytes crossing to HBM. I'll just print that as well for us. So what this is telling us is our arithmetic intensity, so the amount of bandwidth we need is for every flop, we have to do 5,461 unit, every byte, we have to do 5,461 floating point operations. And then if you look at that comparing our hardware can do 275 times 10 to the 12 flops, and it can do 1,230 times 10 to the 9 bytes. So our hardware has about an arithmetic intensity of 223. This workload has an arithmetic intensity of approximately 5,200. And that means when we look at this chart, we're really far all the way out over here, and therefore we're bounded by peak performance. So I think I just use another couple minutes. I'd love to answer any questions here, because I think this is the core thing we're trying to explain here, is any given workload should behave like this line that we see here. And we should be able to just saturate one of the two limits for any given workload. So if any questions, love to answer them here. Otherwise, I think I would just help sketch out this curve for us. And hopefully that will just help us understand as the size of the workload changes, we get to different, we can actually really see ourselves moving across this curve. No, Asaf, that's a really, really great question. So Asaf is asking, is Jax doing something better than the n-cubed matrix multiply? And actually, there are algorithms that are faster in principle than the n-cubed matrix multiply, but none of them are actually practical. The numerical performance degradation is larger than the wall clock speedup justifies. Then also the wall clock speedup is actually very, very small. So this is definitely an n-cubed matrix multiply SF. Cool. let's just now do basically, let's just like sweep this through. So let's do for I, and so matrix dim, let's call it, in range, and let's just do like in 64, 128, 256, 512, 1024. We can go just a little bit higher, 4096. Let's just basically do the same workload. So we can get rid of this. We can keep the step, that seems good. And we'll just want to have a different number of matrices, num matrices. And then we should just at this point, I'm going to just switch us to dtype equals jax.numpy dot bfloat16. So the actual math is happening in these 2 byte types. We'll learn about more of them later. So I think it would just be probably more fair to recall that the total number of bytes crossing to HBM is 2. The total number of flops remains the same. F, we can get rid of this readily. We can just do A times B. I think is equally interesting to us. We can put a jax.jit on F. I think it's good. So we'll apply it like this now. It's a cool way of applying it. Our workload's arithmetic intensity. And then we can just see our performance. Cool. I think I might just turn this off so we don't have to see what it's printing. And we can get average seconds JIT. And we should be in business. So what this should tell us is as we vary the size of the workload, of the matmul. Okay, so this can no longer be this. This has to be jax.lax.batch matmul. So this isn't going to work without that because we need to, instead of multiplying one matrix, we want to multiply multiple matrices. And then additionally, we have to vary the number of matrices depending on our matrix dim. So I think there are a couple ways we can do this. I just want, and the reason I'm just doing this is because I want to keep the number of elements roughly constant. Just so we have the same input. So I will even just put this at 2 to the 20 divided by matrix dim squared to be num matrices. Probably it's a little bit small. 2 to the 20, remember, would be 1,000,000. So maybe I should just make it a little bit bigger. 2 to the 27. Okay, so what this is going to do is just run us through the list of all the matrices as we grow from 64 to 4096. And it's going to calculate the workload arithmetic intensity. And then it's going to show us what flops we get per second and what gigabytes we get per second. And kind of our expectation is at around 256, we'll start to get peak flops. But our flops we get will increase a lot up to 256 and then increase very slowly after 256. And
Robbie,
then,
did you get to do matrix dim squared instead of times 2?
I most definitely did. Thank you. We
I
have
might also need a double / there.
well, I shouldn't, but I will put it there. Oh, I did. Thank you. Because it doesn't round to an integer. Thank you. While we're here, let's just see how big 2 to the 27 is. Oh, it looks like it was a reasonable. So unfortunately, I don't give it any points for the sensibleness of my printing. So let's just upgrade this. We'll print a matrix in. F matrix in. And then we will really matrix in. And let's print some new lines. Just so we can read what's going on. And we can even graph it if we want to. Cool. So the first thing we see that's actually kind of interesting, and I hadn't, it's actually an architectural detail of the chip, is our time actually improves a lot going up to 128, where we aren't able to get that close to the theoretical limit at 64, but we get pretty close to it on 128. And the reason for that is actually entirely that 64 is smaller than the design for this platform. This platform is designed around 128 by 128 nanomolar. So 128 is when we start to get good results. And then as we keep going, we get a gigabytes per second of 825. But our T-flops per second gradually increases. And eventually, we aren't getting very close to the theoretical T-flops per second. I do believe I'm making a mistake. Oh, interesting, because we aren't, oh, excuse me. So there are a couple things going on here. One is we are not multiplying by num matrices. So the total T-flops should depend on num matrices. But then this one is being counted correctly. So hopefully, once we fix that, I'm going to actually go one size bigger just based on those results. They look a little noisy still. Okay, so what this should be showing us is, hopefully once we get the real results, our teraflops per second should get close to the physical limit. But just when we stop getting near the physical limit on our memory bandwidth. Cool. And then I think I like literally am tempted to transcribe this. But let's just see it. So each of our runs is taking about 1 millisecond, which is probably reasonable for micro benchmarking. T-flops per second goes from 3 to now 38, and we're really saturating the bandwidth, 900 gigabytes. Then it goes up to 76, still doing pretty well in the bandwidth. 120, 55 teraflops, we're still much more bound on bandwidth. And then right around 1024, where our arithmetic intensity crosses the 223 that the chip is capable of, we kind of switch. Now we're pretty close on teraflops, but our bandwidth starts to drop. And as we keep going higher, our teraflops per second keeps going up, but our bandwidth per second needs to go down. As the workload arithmetic intensity grows, we switch from being bandwidth bound to flops bound. Cool. So that's really what I'm trying to highlight here. Do folks have any kind of questions, thoughts on this one? Otherwise, I can just give some closing thoughts. And yes, Desperado.
I'm playing around with this on a laptop on a Mac M1, and I'm seeing an interesting trend where it actually, like, the flops go down as it gets bigger. I was curious if you had a quick intuition for that. I realize it's different hardware than what you're playing with here.
Really fascinating. That's Jax with the JIT.
Yeah, I mean, I could be also doing it wrong, but you know,
I do really sincerely hope that you're doing it wrong. There's no reason that should happen. You might I hope when you look at not online, you'll see different things. So just to really send that one out, our system has its inflection point, the one that I'm running on, at 224. I suspect if you understand what's going on in the Mac M1, the inflection point will be at a different point. Probably it'll be a lot smaller, but there should still be the same roofline structure you see. Whereas you keep increasing the operational intensity, you keep getting more performance until you get to the bounded peak. So that you should always see the shape, and therefore growing the matmul should really never hurt performance. It's a really interesting system where that happens, and it might be a bug in the compiler, it might be a bug in your code, but it should be very, very unusual. Yeah, Slava has a good point, which is if it's an M1 Air, perhaps you're thermally throttled. So yes, a server class chip is really designed to achieve good performance for a long time. For a laptop class chip, if the battery goes down or gets a little hot, it can be a little bit different. It's an interesting theory. Carter, could you explain a little bit what you mean when you say the architecture is built around 128D matmul? Yes, so the core of the compute, and we'll learn this more in later sessions as well, is that this compute is optimized for 128 matmul. Because really it's a circuit that actually specializes in doing 128 matmuls. So it can do bigger matmuls by doing a series of 128 by 128 matmuls. But it's really optimized for multiplying matrices that have at least one of their sizes being 128. And then additionally, the way we access HBM actually on this platform is optimized with a stride, trying to grab chunks of 128. So both of those are really optimized for 128. And that's actually why for that 64, I hadn't done that before class. I hadn't even thought about it. But that's why the 64 does so badly, is because we're optimized for 128. Yeah, thank you, Andy. Helpful link from Andy in the chat. Cool. Great questions. Zach?
Hey, Matthew, so does the tiling onto the systolic array happen between SRAM and the MXU, or does this happen like we were talking about before with the kernel, how it you're doing the loop fission and you're just reading over the chunks? Just at what level is the matrix tiled onto the
Yeah,
hardware?
we have like a whole class on tiling and all of those things, but both of them are designed for 8, 128. So things that can be described as 8 by 128. So a 64, there would have been significant ways. I don't know exactly how they would have tried to do it, but there's just no way you can describe a 64 as a set of 8, 128 data loads. Cool. And then I guess I did this exercise before class. I feel like I don't have the heart to during class transcribe the results, but maybe I'll just show them. And this I think is a pretty faithful reproduction of what we just saw in class. So I guess I start with a map-mul dimension of 128. As we grow the arithmetic intensity, we get about the right change in performance. Here we get 255 teraflops. And what I guess I should do is just quickly tell us what we expect. So basically what we expect on the perfect roofline that we saw, this should be just a tiny bit higher. So it should be like up here, 275. And then it should just come down and it should just look just like this. So what I'm trying to highlight, and the whole point of this, is that this whole idea of measuring roof lines and doing this type of analysis has incredibly strong predictive power. And it's not like it's the way these systems are both designed and analyzed is in terms of these roof lines. So no more questions. I just quick note, there's no class next week. I'm out. Looking forward to chatting with everyone on the 13th. So thanks for chatting, folks. I'll stay on the line to answer any more questions people have.